Hello, my name is Micah Richardson, and this is my concept map for the cell membrane. We'll start at the center, which is the plasma membrane, which is the main concept, and we'll build around it. At the top, we'll start with what was called the sandwich model, which was the initial and incorrect model of the membrane. It included membrane proteins that were sandwiched in via phospholipid bilayer. Later on, it was discovered that the membrane proteins in the phospholipid bilayer were actually integrated, and they called this model the fluid mosaic model. Also, an important note, over here we have saturated and unsaturated fatty acids. The unsaturated fatty acids are what give the membrane its fluidity, the double bonds in the unsaturated fatty acids, to be specific. In the fluid mosaic model, you'll see the phospholipid bilayer and the membrane proteins. So we'll go ahead and talk about the phospholipid bilayer for a second. It is made up of hydrophobic tails and hydrophilic heads, and it is an amphipathic molecule, which means that it has both hydrophobic and hydrophilic components. Another example of an amphipathic molecule is a sterol and a glycolipid, which are both also parts of the plasma membrane. So we'll go over here and look at the membrane proteins, and there are two kinds. There's peripheral and integral. Peripheral means that it's outside of the membrane, and integral means that it's inside of the membrane. So some examples of peripheral membranes are glycolipids, proteoglycans, lipid and protein membrane, protein membrane associated proteins. And then the integral examples are transporter, enzyme, receptor, anchor, and monolayer proteins. And integral proteins are special because they can only be broken down by a detergent. And a detergent is a bilayer of the hydrophobic and the hydrophilic components, and they form a cone which break through the membrane. Meanwhile, the peripheral membrane proteins don't require any breaking of the membrane to allow access. And speaking of access, we'll go over here and we'll see that the plasma membrane has membrane channels, such as the ion channels, which are gated, like the gated ion channels, which only allow flow through one way and limit the amount that can come through. Membrane channels are selectively permeable, which means they only allow what they want to come into the cell through active or passive transport. And some examples of passive transport are simple diffusion and channel-mediated passive transport. Both of them are driven by the electrochemical gradient, and it determines the direction of the concentration gradient. So in passive transport, it naturally moves down the concentration gradient from a low solute to a high solute. In active transport, it moves against the concentration gradient, and that requires some energy instead of just being a spontaneous reaction like the passive transport. Excuse me. We'll go over here and we'll see another concept of the plasma membrane, and it's called osmosis, and it's the movement of water from a hypertonic solution, which means that it has a high amount of solute, to a hypotonic solution, which has the more water than solute, and they do this until they can make an isotonic solution, which is a balance of equal amount of solute and water. Also up here, we'll note the vesicles, which is just kind of a side note. It didn't really fit in any of the concepts. It is what helps make new plasma membrane. They break off of the endoplasmic reticulum, and they make their way up to the plasma membrane and form in and make the new layer of the membrane. And that is my concept map. Thank you.